This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss some technology solutions and problem extensions for the 2018 AP Calculus exam, free response question BC6. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing the free response question, and then the scoring guidelines used at the AP Calculus reading. And I'll focus on or highlight the solutions presented in these guidelines, not how the points were awarded. Now, this question was not calculator active. However, I'll show you how to use technology to explore and answer parts of this question and to confirm solutions where appropriate. And because the free response questions are usually very comprehensive, I'll suggest some problem extensions, additional AP Calculus type questions associated with the information given in the problem. And some of these questions may be calculator active. In this last free response question on the BC Calculus exam, often a series question, we're given the Maclaurin series for the log of 1 plus x. And we're told that on its interval of convergence, the series converges to the log of 1 plus x. And there's another function f here, defined by f of x is equal to x times the log of 1 plus x over 3. In Part A, we need to write the first four terms and the general term of the Maclaurin series for f. In Part B, we need to determine the interval of convergence of the Maclaurin series for f. And in Part C, we need to find an error bound associated with the fourth degree Taylor polynomial for f at x equal 2. Part A was worth 2 points. The first point was for writing the first four terms of the Maclaurin series. On the scoring standard, the first four terms are written as part of a sum, but the terms could be presented in a simple list. And the second point was for writing the general term of the Maclaurin series. And the general term could also be presented using summation notation. Part B was worth 5 points. And this is a pretty typical rubric for this kind of a question involving a Taylor or Maclaurin series. 1 point for setting up the ratio associated with the ratio test. That is, a sub n plus 1 divided by a sub n. The limit as n goes to infinity and the absolute value were not necessary to earn the first point. 1 point for computing and sufficiently communicating the limit of the ratio, and there must be some reasonable mathematical indication that the student is evaluating a limit. And 1 point for finding the radius of convergence, and this can be conveyed by actually writing an interval. Note that there was an alternate solution on the scoring standard for earning the first 3 points, and this solution involved the known radius of convergence for the Maclaurin series for the log of 1 plus x. And then the student needs to check the endpoints of the interval. And there was 1 point for considering both endpoints. Now, considering here loosely means actually substituting in each value into the series. And the last point was for the analysis at both endpoints and for producing the final interval of convergence. And Part C was worth 2 points. 1 point for using the fifth degree term on the way to producing an error bound, and 1 point for the final answer. Here's how I can use technology to solve Part A. Using the TI-Nspire CAS, I defined the function f. And then I used the command Taylor. And the arguments here are pretty logical. The function, the variable, the degree of the polynomial, and then an optional argument. By default, the Taylor polynomial is centered at 0. So this command actually returns a Maclaurin polynomial. But we could find a Taylor polynomial centered at any value x equal a. Looking ahead in this question and thinking about convergence, I graphed both the function f and this Maclaurin polynomial over the interval -3 to 3. We can see that with just the first 4 terms of the Maclaurin series, we get a pretty good approximation to the function f. And I think we need to use a little pattern recognition to simply write the general term of the Maclaurin series. In Part B, we need to use the ratio test to determine the radius of convergence r of the series. Using the TI-Nspire, I defined the nth term of the series in terms of n and x. And then I simply found the absolute value of the ratio of 2 consecutive terms, a sub n plus 1 divided by a sub n. Note that since I didn't specify n is greater than 0, the terms n and n plus 1 remain inside the absolute value symbols. Next, I need to evaluate the limit of this ratio. And we know that the series converges when this resulting limit is less than 1. And we can solve this inequality for a more explicit interval. And we can now see that the radius of convergence is r equal 3. To complete the solution to Part B, we need to consider the endpoints of the interval. So using the TI-Nspire, I tried to write and simplify the infinite series when x is equal to -3 and when x is equal to +3. My hope is that I'll be able to identify these series, know quickly whether they converge or diverge, or at least compare the result to a known series. And often the TI-Nspire will actually be able to evaluate the series. When x equals -3, the series looks like this, 3 times the harmonic series. So this series diverges. When x equals +3, the series looks like this. Now, it's a little unfortunate, but very common using technology, to see the cosine of n pi instead of -1 raised to the nth power. This series converges by the alternating series test. And if we really want to see the terms of the series, we can use technology to write a few. This might give us more insight into convergence or divergence, to identify the series, or to compare with a known series. So finally, the interval of convergence of the Maclaurin series is -3 to 3, open at -3, closed at +3. Here are a few problems for you to consider. Write the first 4 non-zero terms and the general term of the Maclaurin series for f, and determine the interval of convergence for each. To solve Part C using technology, I'll use my function a already defined, which represents a term in the series and is a function of n and x. I need the magnitude of the 5th degree term for x equal 2. Note that for n equal 4, a returns the 5th degree term. And this produces a bound on the error of 8 divided by 81. Here are a few more problems that involve a bound on the error of estimation. Each of these series is an alternating series. And suppose we use the first 4 non-zero terms as an approximation to the sum of the series. Find an upper bound on the error of estimation. I hope this video gives you some good ideas for additional practice AP Calculus exam type questions, and of how to use technology to solve some of the parts of this problem, to explore, confirm, and even visualize results. And just a reminder, there are lots of valuable resources on the TI website. There's material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.